Good day, my wonderful viewers. You are welcome to Understanding Chemistry by Nkechi. Today's topic, we will continue with electrolysis, but today we're looking at some examples of electrolysis. So number one, we look at the electrolysis of acidified water, electrolysis of copper 2 sulfate, electrolysis of brine, and electrolysis of molten compound. So if you are not watching a video, if you are seeing this video for the first time, I've done a video on the introductory part of electrolysis, difference between electrolyte and non-electrolyte, mechanism of electrolysis, ionic theory, and preferential discharge of ions during electrolysis. It will be good that you watch those videos before this one. Alright, so let's start. So number one example is electrolysis of acidified water. Electrolysis of acidified water. So what is acidified water? Just water that concentrated, few drops of concentrated tetraoxide of acids has been added to it. So you can also call it electrolysis of dilute tetraoxide of acids. Dilute tetraoxide of acids. So remember in the first video we talked about electrolytic cell. So the special cell designed for carrying out electrolysis of acidified water is called Hoffman voltameter. It's an electrolytic cell. But because of the gases that we produce, hydrogen gas produced at the cathode and oxygen gas produced at the anode. So because of the gases that we collected, if you use the normal medicine that everything is exposed, you can't be able to collect the gas. So this Hoffman voltameter, a special kind of cell for carrying out acidified water. Acidified water contains H2SO4, not hydrochloric acid. The acid that we use is tetraoxide of acetic acid, not any other acids, only this. In case it's in an exam, which of the following acid is used to carry out electrolysis of acidified water? So just know that the answer is tetraoxide of acetic acid. So the ions that are present, for the cations are positively charged. So for the cations here, I have hydrogen ion. So for water, remember water ionizes slightly. I will draw this thing. So water ionizes slightly to give hydrogen ion and hydroxide ion. So for the anions, so you have SO4 2 minus. You have OH minus. So at the cathode, what happens at the cathode? The hydrogen ion will migrate to the cathode, negative electrode. Remember, reduction takes place at the cathode. So they're going to accept electron for the cathode and become discharged as neutral atom, neutral hydrogen atom. So neutral hydrogen atom will pair up to form the atomic molecule of gaseous hydrogen. So let's write the equation. So it's good to know how to write an equation at the cathode and anode. Very, very important. So this hydrogen ion. So at the cathode, a neutral hydrogen atom, then the electron. Oh, sorry. If you're writing, look at this. I have plus here, I have minus. It's not correct. So if you're writing for the cathode, you put the electron on the left hand side. So this, so as you can see, plus minus is 0 because there's no charge on this atom. If I put it the other way, it's wrong. Plus minus. So this neutral hydrogen atom will pair up to form the atomic molecule of hydrogen, gaseous hydrogen. Sulfate ion and hydroxide ion is going to migrate to the anode, where this hydroxide ion will be preferential discharge because it's higher in the geochemical series than the sulfate ion for the anions. So this one is preferential discharge. So when anytime OH minus is preferential discharge, oxygen gas is what produced. That's the product we get there, oxygen gas. But what happens is that the oxygen, the hydroxide ion will first of all form hydroxide group, and hydroxide group will not pair up with each other. You have two hydroxide group will now combine to form one molecule of water and one atom of oxygen. Of course, one atom of oxygen is not atomic oxygen is not stable, so it's going to pair up to form one molecule of gaseous oxygen atom. Okay, let's look at the equation for the reaction at the anode. So this is hydroxide ion to form OH group without any charge. So what happens if I write this thing here? If I put electron here, look at this. If I put electron and not put anything, it's wrong. Minus 1 minus 1 will give me minus 2, and here there's no charge, so it's wrong. If you are writing for the anode, you put your electron on the right hand side. So minus 1 minus 1. So this OH will combine with another OH to form 1 mole of water. 1 mole of water and atomic oxygen. So this one is not stable, so it's going to combine, pair up to form oxygen atom. Okay, I want to establish something. Because if you check our textbook, anodic half equation and cathodic half equation, you will see that they not use this one. They didn't do it like this. Just put one equation. So I want to show you how that equation is being derived. Okay, look at this. This is the product oxygen. So from this point, if I put oxygen here, my oxygen here, assuming I want to balance this equation and put my oxygen here, I have how many oxygen atoms? 3. I have 2 hydrogen atoms. So I want to balance oxygen. If I put 2 here and I put 2 here, so I have and I have what? 4 atoms of hydrogen. 2 plus 2. So what do? I will put 2 here. If I put 2 here, let's see the equation in the balance. 2 plus 2 for oxygen, 4. 2 oxygen plus 2, that is 4. What of hydrogen? 2 hydrogen, that is 4. 2 times 2, that is 4. So it's balanced. So what do I do now? Okay, look at this. If I have 2 hydroxide and I have 2, that is what I have here is 4. 4 moles of 2 plus 2, that is 4. Since I have 4 here, 2 plus 2, that is 4. I'll put 4 here. So of course I want to balance this, I also put 4 here. And I want to balance, I have 4 minus. Here I have only 1. I also put 4 for the electron. So you have seen I have balanced this thing. So which means if I want to also balance this electron for the anodic half equation, since I have 4 electrons here, I will also come here and do what? And put my 4. That's what it means. I put 4. Yes, I'll put 4 here. Let me expand this thing. So if I put 4 here, I also put 4 here. That's what it means. I'll put 4 there. So in the anodic equation, this is how this anodic equation is gotten. So anodic half equation, you have 4 hydrogen ion plus 4 electrons to give you, of course, is what you get hydrogen gas is what you have gotten. But what I've got hydrogen, so I'll put 2 H2. Of course, if I have 2 here, just to put 2 and put 2. Then for the cathodic, this cathodics. Okay, anodic anodic half reaction. At anodic half reaction, remember 4 hydroxide ion will migrate to the anode and become discharged as oxygen gas and water. Okay, look at this. So 4 hydroxide ion, 4 moles of hydroxide ion. This 4 hydroxide group is what pair up 2 to give 2 moles of water and 1 molecule of oxygen. So I'll no longer put this one here. I will not, this one and this one are the same thing. So it's the product I'm going to put. So I'm going to put this one plus then the electron. I'll put the electron. 4 moles of electron. So what happened is that you look at over at times I can be asked to write the reaction at the cathode, anodic reaction at the cathode, reaction at the anodes, and the overall reaction. So for the overall reaction is the sum when you add the algebraic sum of the cathodic half reaction and the anodic half reaction. So we're going to sum them together and cancel out the electron. The electron will not appear in the overall reaction. So 4 moles of hydrogen ion, 4 moles of hydroxide ion, 2 moles of water plus 2 moles of hydrogen gas plus 1 mole of oxygen. For the cathodic half reaction, the 4 moles of hydrogen is this. This is the electron. These 4 hydrogen moles of hydrogen atom, you see here, neutral atom, hydrogen atom, see here, is what produces, is what is something as this. 2 moles of H2H. So this and this are the center and they produce this. So I no longer put this thing here. So what they produce is these 2 moles of hydrogen gas. That's what I put here. So I know because that this needs to confuse students. They ask the teacher, how did you get this anodic reaction? How come? How from here? How come from these 1 mole of oxygen atom? How did you get this to this? How did you get this for? Where is this for coming from? So that's how it came about. So, and I mentioned that for the analysis of acidified water, hydrogen ion and this hydrogen goes out as a water molecule. The solution will become more concentrated, Then the amount of acid that I have here will remain the same. When I mean the amount of acid, the number of moles of acid that you have in the solution will remain the same. But the concentration has changed because of removal of water. So let's look at another example. The doses of copper 2 tetraoxide 6 using different anodes. So number 1 anode, we are going to use graphite as the anode, but copper is the cathode is copper cathode. So we're going to use different anodes. So number 1 is a graphite anode or carbon anode. So number 2, we also use copper anode. So what happens using graphite anode? So copper 2 tetraoxide 6 solution. Okay, so you have your SO4 and also have water. The cations, let's look at the cations we have. For cation is copper 2 ion. For water, you have hydrogen ion, that's cation. For the anion, SO4 2 minus and hydroxide ion. Let's look at what happens at the cathode. At the cathode, what will happen there? At the cathode, these cations, remember cations, cathode ions, that's what cation. So copper 2 ion and hydrogen ion, the two will migrate to the cathode. Which of them is going to be preferential discharge? Remember, so for the cations, we will talk about factors that affect discharge of ion. Number 1, position at the electrochemical series and concentration of the ion. So these two and this, when it comes to position, copper in the chemical series, you have hydrogen ion, you have copper ion. So this one is lower in the chemical series. So it's going to be a preferential discharge. And also, when it comes to concentration, copper 2 ion has a higher concentration and they are closer. So concentration effect also is going to also work out because they're closer. So copper ion will be preferential discharge over hydrogen. And what happens there at the cathode? Reduction takes place at the cathode. So copper ion is going to accept electron from the cathode and become deposited as neutral atom, which is copper metal, metallic copper. So this is the way. Remember, if you write this thing like this and put this, just know you are wrong. 2 plus 2 minus, it is wrong. So for the cathode, put your electron on the left hand side. So 2 plus 2 minus is 0. This compound doesn't have any charge. So at the anode, what happens at the anode? Oxidation always takes place at the anode. So this is sulfate ion and hydroxide ion. So the one that will preferential discharge is sulfate hydrogen ion. Hydroxide ion will preferential discharge because it is higher for the anions. The one that's higher in the chemical series will be preferential discharge. So hydroxide ion will give hydroxide group plus this electron. So the 2 OH group combine to give water and atomic oxygen. So the atomic oxygen is not stable. So it's going to pair up to give oxygen gas. Okay, so what we have here is same with the other one. We are going to have anodic. Let's look at the cathodic half reaction. Cathodic half reaction. So you have cathodic half reaction. Cu2 plus 2 electron to give Cu. So anodic half reaction. Anodic half reaction. So hydroxide, remember when you balance this thing, if I put this in, I have it like what we do the other way. Anywhere you have hydroxide, it's always 4 moles of it. So look at these 2. If I bring these 2 up here, I could do the other this thing, I put 2 here. I'll be having 2, I'll be having 2. And as I have 2 here, I'll have 4 here. And I'll have 4 here. So for anodic half reaction, 4 moles of hydroxide ion give 2 moles of water plus 1 mole of oxygen plus 4 electrons. So for the anodic reaction, if you want to get to overall reaction, your electron loss and electron gain must be the same. So the electron I have at the cathodic half reaction must be the same with the anodic half reaction. How do I make this electron to be the same? Simple, by multiplying this by 2. So multiply this thing by 2, I'll be having 2 moles of this, 4 electrons, and 2 moles of metallic copper. So I will now combine the 2 equations to get overall reaction. Remember, we don't have to add the electron. We'll not add it to cancel out. So this overall reaction. Okay, let's look at this ion. I have copper 2 ion, and this one was discharged as metallic copper, and this one is discharged as water and oxygen gas. What's the color of copper 2 tetrasulfate solution? Of course, it's blue in color. The color is blue in color. So this one is being discharged, and this one being discharged. The solution, we have hydrogen ion and sulfate ion. So that solution is going to be acidic, and you will see it by the gradual fading away. For no, that blue color will be fading away, fading away, fading away, fading away, gradually fade away. So it means the solution, what I have there, and if you continue the electrolysis, not stop it, because I have dilute terrace of a cyst. It will not continue. It starts doing having what electrolysis of acidified water will start up immediately if you do not stop the process. So the point I want to make, at times they can ask you about the solution. What happens to the solution of this at the end of the what solution is going to become? Is it alkaline? Is it going to be this? So just know when this one is out, the solution will be what? Acidic. So what happens when we use copper anode to carry this electrolysis? Let's look at the ions. These two ions, copper 2 ion and hydrogen ion, the two are going to migrate to the cathode. What about the cathode? Reduction state of the cathode. Where they're going to do what? Accept electron for the cathode. Which of them will preferentially discharge? Of course, it's copper, because it's lower in the chemical series for the cations than hydrogen. So copper 2 ion is going to be preferentially discharged as a neutral atom, that's a copper metal, and deposited at the cathode. So let's write the equation for the reaction. Let's look at the anions. You have sulfate ion, you have hydroxide ion. Remember that the copper, we are using copper anode. And I mentioned the factors that influence state of ion. We mentioned that nature of the electrode. Because I is using copper anode, that copper anode is going to take part in this electrolysis. It's going to dissolve in the solution to form copper 2 ion. So 3 things are possible here. Let's look at the 3 possibilities. This one that's never discharged can be discharged. This one that's already discharged can be discharged as a salt. That's what they call sulfonation. Sorry, as salt. Hydroxide ion can also be discharged. Hydroxide ion can also be discharged. Then that electrode, the copper electrode that dissolves inside solution, that give up an electron and dissolve in the solution to form copper 2 ion. These are the 3 possibilities. These are 3 things that can happen, but this particular one, copper anodes, the anodes dissolve into the solution to form copper 2 ion. It takes a lesser energy with ease, lesser energy for this to happen. So this one take a higher energy. So the one that will be preferentially discharged, the one that will take place at the anode is this. The copper anode dissolve in solution to give copper ion, copper 2 ion plus electron. Okay, so let's look at the overall reaction. Because what I have here, 2 electron, 2 electron. Overall reaction will not be algebraic sum of the 2 reactions. So look at this equation. Copper anode dissolve in the solution, and the ions migrate to the cathode, where they are deposited at metallic copper. So what happened to the electrolyte? The electrolyte, the concentration of electrolyte remains the same. The color of copper sulfate, the color of copper 2, the rest of a 6, which is blue in color, will not fade. It will remain the same, because it's just a transfer of what? Copper from the anode to the cathode. Transfer of copper from anode to the cathode. So the color, the blue color will not fade, it remain the same. Look at this, look at the electrolytic cell. What will happen to the mass of the anode? The mass of the anode the mass of this anode is going to increase. You can see the mass, the cathode. Look at the electrode for the anode is depreciating, decreasing in size, because it will dissolve in solution at copper ion and it will be deposited here. So at the end of the reaction, the mass of the cathode will increase in size, while there will be decrease in size of the mass of the anode. The doses of brine. What is brine? Brine is concentrated sodium chloride using carbon electrode. So I have sodium chloride. Of course, there is water in it. So what are the cations? Let's look at the cations. Sodium ion. The ion from water, hydrogen ion. That's cation. Let's look at the anions. Chloride ion and hydroxide ion. So this is brine. At the cathode, what happens at the cathode? Sodium and hydrogen ion. Remember, the electrode that we are using is graphite electrode. This is the inert electrode that don't take part in the electrolytic reaction, that inert electrode. So if you are asked to give two examples of an inert electrode, so you can give carbon, platinum. Okay, look at this. Sodium and hydrogen ion, they're going to migrate to the cathode. Which of them will be preparing discharge? Of course, in terms of concentration, the ion coming from this salt is highly concentrated than the one coming from water. But in the electrochemical series, you have, for the cations, sodium is high in the electrochemical series and the hydrogen is lower in the electrochemical series. So in terms of concentration, we know that the one that is highly concentrated will be perpetually discharged, right? But because of this distance, sodium is high in the electrochemical series and hydrogen is lower. Because they are far apart, effect of concentration will not hold. We cancel out. What we use is position. So according to position, the ions that are lower in the electrochemical series will be perpetually discharged over those that are what? Higher in the electrochemical. So this one will be discharged as hydrogen gas. So let me write it there. At the cathode. So hydrogen gas will be liberated. So at the anode, what happens at the anode? At the anode, look at, they have these two ions, chloride ion and this. Two of them are going to migrate to the anode. Which of them will be perpetually discharged? Remember, the concentration of chloride ion coming from sodium chloride is higher than this. And then when it comes to the anions in the chemical series, they are closer. Because they are closer, effect of concentration will take preference over position. If it's position, this one would have been discharged because it's higher up for the anions. But because of this one is highly concentrated and they are also closer, concentration takes preference over any other thing if they are closer in the chemical series. Because they are closer, so chloride ion will be perpetually discharged and it will discharge as chlorine gas. So chloride ion as chlorine gas, with the chlorine is the atomic molecule plus, okay, let me write this way. Okay, plus electron. So I'll balance my outer. I have two chlorine atoms here, so I'll put 2 here to balance it. Also put 2 electrons. So because I have 2 electrons here, so look at this. Anodic reaction, cathodic reaction. What I'll just use these 2 to multiply here, so I can have 2 electrons. So anodic, let me say cathodic. Cathodic half reaction. So they ask to write the equation as the cathode and anode. You can write this one. You are correct. You can also write the cathodic half reaction. You are correct. But when it comes to calculation, using calculation, if you are solving calculation that involve a process of brine, a process of acidified water, use the cathodic half reaction because of the number of electrons I'll be working with in your calculation. So cathodic half reaction. So these 2 multiply this 2 hydrogen ion plus 2 anodic half equation, half reaction. Two chloride ion to give chlorine gas plus 2 electron. So let's look at the overall reaction. Volume of hydrogen gas and 1 volume of chlorine gas is what is obtained. Okay, let's look at this electrolysis again using another electrode, using mercury cathode. If mercury is the cathode, what will happen? If mercury is the cathode, so let's look at it. Ion and hydrogen ion will migrate to the cathode. Which of them is going to potential discharge? Of course, the first one we did using graphite as cathode and anode. Hydrogen ion was potential discharge as hydrogen gas. But in this case, yes, hydrogen ion is supposed to be potential discharge because it's lower in the electrochemical series, even though sodium is highly concentrated because they are far apart. Because of mercury, you're using mercury cathode. Mercury will influence this reaction. Mercury is going to take part in this electrolysis. It's going to take part. So mercury has a strong affinity for sodium ion. 2 of them are 5 and 6. They don't joke with each other. Even though sodium is never, sodium ion is already discharged because of strong affinity of mercury and sodium. So sodium will be discharged. Sodium ion will be discharged. So this sodium ion plus mercury. So remember, we say the nature of electrode influences. It's one of the factors that influences the size of ion during electrolysis. So accept electron, and they're going to form association called sodium. This sodium amalgam. A loose association called sodium amalgam. The special cell that's being used for this reaction is what we call Kellner. Take note of that. Those are very for jam. Kellner Sauvé cell. So this is kind of special cell that's being used for this electrolysis. Kellner Sauvé cell. Okay, look at this. So this liquid, this sodium amalgam, remember they form loose association. So the sodium amalgam will be dissolved in water. That's it. If you check at that cell, that's the place that water will be flowing. So when water flows, react with this. So to give you sodium hydroxide, hydrogen gas, and mercury. Okay, look at this. So the question is balanced. All right, so this is what I have. What to be obtained? So at the anode, is it the same thing? That you have chloride and you have hydroxide ion. Of course, this one will be discharged because of concentration and because they are closer. So chloride ion, chlorine gas, So this is what happens at the cathode. This is what happens here. So as you can see, what happened is that the product of electrolysis of brine is the same thing with that the one you got from using mercury cathodes and the one you use graphite electrode. They are the same thing. So what are the products? Sodium hydroxide. Sodium hydroxide. These are the product of electrolysis of brine. Sodium hydroxide, hydrogen gas, and chlorine gas. So these are the major product that has been produced. This mercury is very expensive, so it can be reused again to carry out this water electrolysis. The one who use, I missed out something there. The one who use the graphite electrode to carry out graphite electrode. The one who use graphite electrode, what was discharged was hydrogen ion, isn't it, as hydrogen gas. And at the anode, this one was discharged as chlorine gas. And the solution, what will be left when this one is out and this one is out, what will be left is sodium hydroxide. The version of sodium hydroxide, electrolysis of brine. It's one of the method of preparing sodium hydroxide in a large scale. What of chlorine gas? Still electrolysis of brine. What of hydrogen gas? You also see commercial version of hydrogen gas. It's also electrolysis of brine. So when this one is out of the solution, what will remain there is sodium hydroxide, which means the solution will become what? Alkaline. Okay, let's look at other examples. Let's look at the products of electrolysis of these electrolysis solutions we have here. We have copper 2 chloride solution. What are the products that we gotten? Okay, let's look at this number 1. So copper 2 chloride. This is copper 2 chloride. Aqueous. So let's look at the. Remember, water is present. There's water there. So this the cation, this anion. For the water, I have this and I have this. If we use graphite, remember, because of copper, if we use graphite inert electrode, graphite or platinum, this at the anode, this one will be at the cathode, this one will be discharged as copper. So we're going to get copper. If you use graphite electrode, if you use graphite anode, so you have copper at the cathode. Then this and this, the one that will first discharge, when you have chloride ion and hydroxide ion, what will be discharged is chloride ion will be discharged as chlorine gas. So as chlorine gas, so chlorine gas, you get chlorine gas at the anode, copper at the cathode. So what happens when you use copper anode? It's the same thing you did in the electrolysis of copper 2 sulfate using copper anode. The same thing you will get. So you get copper at the cathode and copper at the anode. Okay, this is electrolysis of concentrated sodium hydroxide. If we use graphite electrode, inert electrode, if we use graphite electrode, so this and this one is highly concentrated because of the distance, they are far apart. So hydrogen gas will be discharged at the cathode. So at the cathode, they have hydrogen gas. At the anode, of course, the ions are the same. So what we have is anytime hydrogen ion is being discharged, it's said as oxygen. So you get oxygen. You get oxygen at the anode. Concentrated hydrochloric acid. These are the ions.
Thank you, my wonderful viewers, for watching this video to the end. So next video, we're looking at calculations involving electrolysis. We're solving so many problems involving electrolysis calculation. Okay, thank you for watching. Have a great